Hi, how is everyone? Great to see you all again. So today we're going to be investigating a phenomenon called the photoelectric effect. So before we dive in, can anyone guess what that word actually means based on its components? Yeah, thanks, Michael. Well done. So photo is the Greek word for light, and electric's pretty obvious. So if you put them together, you get light making electricity. Specifically, Specifically, the photoelectric effect, it's a phenomena where light or any other electromagnetic radiation strikes a surface and electrons are emitted as a result, called photoelectrons. Josh, can you tell me, please, what would be the energy transformation going on here? Yep, that's right. So electromagnetic energy into electrical energy. So I'll just let you have a quick read of the syllabus points that we'll be covering related to the photoelectric effect. So there's the inquiry question, the content dot point, and the skills dot point. What you should recognize is that this is actually some content that you've been asking me about for quite some time. It's to do with the reconceptualization of light and how physicists changed the way they thought about the model of light. So for example, you guys have often asked me, how can light be a particle? How can light be a wave and a particle? It's a strange thing, and that's what we're going to be covering today. And I think the reason you ask me those questions is because of what you see in certain modern TV shows. I'm a fan of the Big Bang Theory. I know you guys are as well, but it does have a tendency, I think, to let certain scientific cats out of their bag in terms of the mysteries that we find, but not necessarily explaining them all that well at the same time. So this picture is from one of my favourite episodes. It's the one where Sheldon is trying to use the balls from the ball pit as models as he tries to solve a problem to do with why electrons sometimes behave as if they have no mass. And the solution to that problem ultimately turns out to be a very enigmatic concept called wave-particle duality. Anyone know what this means? Yeah, thanks, Lily. So, as I suspected, this isn't exactly new to you. Wave-particle duality refers to the observation that light sometimes behaves like a wave in some circumstances, and in other circumstances behaves like a particle, or it behaves like a wavicle, as one of my former students some time ago said quite frequently. Now, sometimes people misinterpret this information to mean that light is sometimes a wave and at other times changes into a particle, whereas that's not quite the case. Light is not strictly speaking particles. It's not strictly speaking wave-like in nature, but it's a combination of both all the time. So it's wave-like and it's also particle-like. Is this duality only seen in light though? No, you're right, Grace. Well done. Yep, so you've referred to Sheldon's thought experiment in which you've got electrons behaving as if they have no mass. What they're actually doing is they're exhibiting wave-like behavior in that instance, whereas we traditionally think of them as being particles, which is how they behave most of the time, in certain circumstances, I should say. In fact, the wave-particle duality is everywhere. All types of matter and energy, as they move around and as they interact, they exhibit this wave-particle duality. But it's really only evident when you get down to what we call the quantum level. This is the level where you've got the smallest possible amount of matter or energy. So the reason this concept is such an enigma is simply because we don't observe the duality at a kind of macro level, at everyday experience. The other problem is that your teachers in year 7 to 10 actually lied to you when they told you, or at least implied, that particles and waves are separate entities, when in fact they're not. So feel free to blame them the next time you see them. So if this duality is only evident at the quantum level, then how do we know that it exists? Any ideas? Yeah, thanks, Josh. Yeah, that's good. So many experiments have been done over time, producing results that can be observed at the macro level, which are related to this duality. So the true nature of energy and matter can only be inferred by observing its behavior on a macro level in various situations. What are some of the different behaviors that light exhibits that indicate its wave-like nature? I'll give you a minute to think about that. So obviously there's reflection. There's also refraction. So when light bends as it crosses the boundary between two media, and that's because the wavefront reaches the boundary at different times, resulting in that bending. There's also, yep, thanks very much, Grace, interference and diffraction. So the double slit experiment is one in which light passes through two slits, and the light wave spreads out from the two different slits, and the two spreading waves will interfere with each other, producing constructive and destructive interference, hence the interference pattern. What else is there? Yeah, thanks, Michael. We've also got polarization, which is obviously where the transverse oscillations of the light wave can be restricted to a single plane. Now, what all these behaviors have in common, and there's others like them, is that they can only be best explained by inferring that light is wave-like in nature. But so that's sort of where it stood at the end of the 1800s. But now that we know in the 21st century, that's not the end of the story. So what I want to get you guys to do is to get into the mindset of a physicist who lived and worked end of the 1800s, beginning of the 1900s, working through the minds, and they were working under the assumption that light was purely wave-like in nature. Okay, so where that started to fall apart a little bit is with certain experiments related to the photoelectric effect. And you guys are going to repeat those experiments and try and sort of think through the results as they did 100 years ago, and see if you can be figuring out and working out how the model of light changed. So I'll show you this applet. If you can all get this applet up in front of you on your screen, just by following the link. I'll bring it up here as well. Okay, so here we're able to do experiments related to the photoelectric effect. You can expose a metal plate to electromagnetic radiation and you can get a photocurrent. You can also manipulate certain variables, as you can see within the applet, which will then influence the photocurrent. So who can tell me the variable which refers to the one that's manipulated and changed? What's that one? Michael? Yep, it's the independent variable. Well done. Grace, what is the variable which we measure, the one that we expect to be affected by the independent variable? That's right, dependent. Now, as you go through this, I need you to only manipulate one independent variable at a time and keep everything else the same. What do we call that, Lily? Yeah, thank you. Yeah, that's the controlled variable. Well done. All right, so bottom line, what I need you to do is to note down the changes in the photocurrent that occur when you manipulate these independent variables. Also, I want you thinking about how do these observations help us to reconceptualize the model of light? Go for it. Okay, so what have we got? Grace, do you want to go first? Okay, so you found that as you increase the wavelength, the electrons get slower. They lose kinetic energy. You've also found that as you decrease the wavelength, the electrons get faster. They get more kinetic energy. Josh, have you got anything to add to that? Yeah, you're right. So changes in wavelength correspond to changes in frequency. So as we decrease the wavelength, we're increasing the frequency. You're right, yeah. So we can say that the frequency seems to be proportional to the kinetic energy of the electrons, but we'd have to, or at least their speed, but we'd have to do further numerical investigations to confirm that relationship, which we will. Michael, have you got anything to add? Great, great. So you found that there's a certain wavelength or a certain frequency, which would correspond to, at which the electrons stop and there's no electrons being emitted. So we're pretty much at that wavelength here for this metal. So what we call that is the threshold frequency. Lily? Yeah. So you found that if you change the metal, the threshold frequency changes. That's right as well. Well done, everybody. Let's keep going. Let's find some more.